Okay, we're back and we're doing some projectile motion. And in this one, I just want to make a short video to show and try to explain and understand why is it that projectiles, like when you throw a ball or something, it follows that classic arch type curve. Now technically it's a parabola under ideal conditions. Now by ideal conditions I mean if we ignore air friction. Okay, so imagine you have like a ball rolling on a tabletop, and you can magically flip a switch that turns off the Earth's gravity. And again, remember, we're talking about this with no air friction right now. The ball on a tabletop, if the table is flat, has a constant speed going sideways, a constant horizontal velocity. And it doesn't matter what that speed is, what the number is. What would happen, though, is if you could look at it when it flies off the table, and there's no gravity, of course it's not going to fall, it should just keep going in a straight line at that same speed. That's the law of inertia. Okay, there's no sideways forces acting on it. Now imagine if you took a snapshot every second, or if you had like a strobe light that was flashing every second, and you could see the position of the ball. After the first second, it moves a certain distance, and maybe the ball is at that position with the red X. Now, every second afterwards, as long as it's the same time period, because it's moving at a constant speed, it'll move the same distance every flash of that strobe light. Okay? Just basic constant speed, constant velocity, going sideways. Now, flip the switch back on and turn Earth's gravity back on. Instead of rolling the ball off the tabletop, imagine you just hold it right at the edge and just simply drop it so it falls straight down. With gravity being a net force, Newton's laws tell us that it'll accelerate. So after the first second, if it's falling, it falls just a certain distance, a small distance, after the first second. And maybe it's fallen to that green X. Now the next second, okay, when the strobe light flashes again, it speeds up so it falls a little bit farther. And the next second it falls even farther. Maybe it's way the heck down here somewhere. And so on. Okay? What projectiles are, what projectile motion is, it's the combination of these two motions. A constant velocity going sideways, okay, so the same distance every second, and a constant acceleration vertically as it falls, okay, the green X's. Put those two together, make it look like a grid now. After the first second, as it now is rolling and flies off the tabletop with gravity, it moves that distance forward, but also falls a certain distance, so the actual position is the blue X. The next second, it keeps moving forward, but now it falls a little bit farther. The actual position of the ball is down here. The next second goes the same distance forward, but now it falls an even bigger distance, so the actual position of the ball is here. And so on. Okay, and if you let it fall far enough, it'll just keep doing that over and over and over again every second. Look at the path that those X's, the blue X's, map out if we connect all the dots, as they say. Okay, it starts horizontally off the table, but then with the influence of gravity, as it moves forward, the actual path, if we did this to scale and actually measured it, would be a perfect parabola, it turns out. Okay, that's where the arch comes from. That's where the parabola comes from that you see projectiles follow. Okay, now let me switch. This is a simulation that's called interactive physics, and I'm just going to run it. It's like kicking a ball or something off the ground, and this was with no air friction or anything, and we can actually see that beautiful parabola up here, that perfect arch. Okay, And what the simulation shows are the velocity vectors is the blue arrow. Okay, it's changing as it goes. It's two-dimensional motion. And a constant force of gravity causing that constant acceleration going downward. Okay, a constant horizontal velocity, though. Well, watch what happens. Let's consider air friction now. Okay, air friction depends on your velocity. So if you have any sideways velocity, that means you're going to have a sideways force, a horizontal force. So not only does gravity affect it up and down, but now air resistance is affecting it both vertically and horizontally. That destroys what you need to form the parabola, because now your horizontal position isn't the same every second. It's going to be changing because now you have air friction. You have a second force acting on it, part of which is going horizontally. So in the simulation, this is nice. I can go ahead and I can add some air friction now. And it doesn't really matter what these units are or anything, but we just turn on air friction. You can do that in computers. We can make it a little more realistic. Okay, now with a lot of air friction, if I run it again, notice how different it is. It launched at the same speed and at the same angle. But now air friction, it's that rubbing. Okay, you're losing energy. You're losing speed. You have this other force acting on you. It's more complicated. It's a non-constant force, which is why we tend not to deal with it very much in high school classes. But notice that the shape of the arch is no longer perfectly symmetric. It's a little longer on the right half compared, and it gets shortened up on the left half of the arch as you go. Okay, so air friction is definitely complicated. This is more realistic. You don't really have perfect parabolas on Earth because we have air all the time. If we threw something on the moon with no air, you'd have the perfect arch, the perfect parabola. Here on Earth, even though it might not be this extreme, I really wanted to have you see the difference between the shapes of the trajectories with and without air friction, and just appreciate how complicated air friction can be on objects. For those of you who are interested in aerospace engineering, or designing planes or rockets or things like that, air friction is a big deal, and you use computer simulations and all sorts of experimentation techniques to learn how to adjust for it and how to have things not burn up if they're going at high speeds and experiencing this rubbing through the air. Okay, so hopefully you have a sense of why there's an arch in the first place, and also have an appreciation for how air friction can change that arch in real life. Okay. Yeah, so I hope all is well. I hope this makes a little bit of sense, and until next time, we will see you later.